Okay, so thanks for inviting me to talk about three-dimensional extinction mapping. So yeah, I'll be a little bit not the same scales that we just heard. I'm looking at disks as well, but it's the disk of the galaxy. And so here's an image of the Sombrero galaxy showing a bit the difficulty that we have seeing the structure of our own Milky Way as we're in it. So let's see, what will I talk about today? First of all, it's going to be about four points. I'm going to go through what extinction mapping is, what we've got, as to say, what data we're using at the moment to do the mapping. And then I'll talk about the maps that are being produced, and then I'll finish off with what we can do in the future, or what we would need in terms of data. Okay. So the main ingredient in 3D extinction mapping is stellar catalogs. We need stars because we're interested in extinction, which, as you all know, I think, will absorb and diffuse electromagnetic radiation coming from the stars. So in the optical, here on the left, the visible, you see it's all dark. Its wavelength dependency means that in the infrared, we can see through these clouds. But any stars that are affected by extinction will be dimmer and redder. So if we know the intrinsic color of a star, we can get its extinction. This is, of course, a 2D measurement. If we want a 3D map, we have to have some way of getting to the third dimension, some sort of estimate of stellar distances. But in the end, what you're trying to do is get a line of sight distribution of the extinction as a function of distance. As you can see here by the points here, and then the extinction as a function the extinction per unit distance will give you an idea of the dust density as a function of distance. So that's the main aim of extinction mapping. And why do we want to do it? Well, one could argue that we still know nothing about the galactic structure, which isn't entirely true. I'm being a bit provocative, but we often, when we're talking about the galaxy, we look at a map like this, or this one in particular, and say, okay, the Milky Way, here's our observations, this is where they are. And we have to remind ourselves it's an artistic impression of the galaxy based on data, but still there's quite a large possibility that our galaxy does not look like this. And in fact, galactic astronomers are a little bit like 15th century geographers, producing maps like this, where we're missing continents. The ones that we do know about are a bit deformed, and we're not entirely sure how they're all linked up together. So that's kind of where we're at the moment. So we could say, well, we've got kinematic distances. They can be useful. I won't go into much detail here, but of course, with kinematic distances, you get a radial velocity of a emission line. And if you know the galactic rotation curve, you can get a distance, a galactocentric distance. And that can be useful, except when you're in the inner galaxy, because of course you have two solutions to that. Which means you're not clear if you're at a near distance or a far distance. Because this was first started in the 50s, and they thought that within 10 years, the galactic structure problem would be solved. And here's the first map in the 50s from Van der Hulst, and you see the inner galaxy is missing because it's just too difficult to do. And a more recent map in 2006, the inner galaxy is still missing, although we can start seeing some structure that we can interpret in terms of spiral arms. But it's still difficult when you go towards the anti-center, towards the center, where radial velocities due to galactic rotation tend to go to zero. So kinematic distances are good. Extinction distances are a very good complement. Here's an example from just 2 years ago from Catherine Zucker and collaborators. So looking at different molecular regions, you can see in the top panel, the plane of the sky showing different regions and color-coded. The bottom panel shows you their longitude and their distance on the right-hand side. What I need to point out here is that, in fact, the error bars are included in that plot. They're just so small that mostly in the symbols. So it's we're getting some very good distances that we weren't able to do with kinematic distances. And in fact, Catherine went a step further, and this year managed to provide distances along filaments, so you can get a relative orientation of the filaments along the line of sight. So for Perseus on the left, for example, you get a 20 parsec gradient going from lower galactic latitudes up towards the plane. So we can see that the methods and data exist to do this kind of precision distance estimates. However, most of these are concentrated around the solar position, which is still very useful. But if we really want to try to put everything into context, into a galactic context, we need to look more in the galactic plane. In this way, you can look at ISM conditions with respect to spiral arms, maybe even see what happens as we go through an arm, which, as we've seen in the last slide, could maybe be possible in the future, but existing 3D maps are not capable of doing that. So this is why we want to do extinction mapping. And so what data are we using currently to do this? I'm not going to mention all the data. I'm going to look at some of the bigger surveys. So in terms of ground-based visible surveys, you have the Sloan Digital Sky Survey, which is deep and could be useful, but it's mostly focused on extragalactic studies. So as you can see in the footprint on the bottom, sorry, on the top left, it's on higher galactic latitudes. The plane is avoided except for certain slices, which are part of another survey called Segway. So I'll leave SDSS aside for the moment. Pan-STARRS is another survey which is very useful for this kind of effort. It's in Hawaii, single telescope, so we don't have anything below declination of -30, but it's got a huge field of view and a fast integration time. And so we're basically getting 3 square degree image every minute over a night. So they're producing about 10 terabytes per night. In fact, their latest release, I think, is the largest astronomical catalog release in history. So there's many petabytes. Anyway, so we get arc-second seeing down to 20th magnitude, and it's the same filter set approximately as the Sloan, as you can see in the transmission filters here. So that's for the visible. Near infrared, of course, is interesting because, as I said at the start, we go through deeper, denser dust clouds. So the 2 micron all sky survey, two telescopes, it was done quite a long time ago now, but lasted 4 years in 3 infrared bands, down to 14 magnitude in K. And as you can see, while the bulge is much more visible than it is in the visible range. So that's useful. It's not as deep, but like I said, we see through denser clouds, so that is good. As far as other surveys go, there's some more recent work done in ESO with the VERCAM and UCURT with WFCAM in southern and northern hemispheres, respectively. They've got JH and K, they add Y and Z, which is a bit more towards the visible. The thing is, they haven't done a single survey. It's many separate heterogeneous surveys, sometimes in 2 bands, sometimes in 3 bands, 5 bands, different limiting magnitudes. So it could be useful, but for the moment, it's a bit patchy. The big survey at the moment is ESA's Gaia mission, which is in the visible. Launched in 2013. It finished its 5-year nominal mission a couple of years ago, but it's got an extension. I think the latest catalog, the final catalog won't be out until about 2028. And its main objective is looking at many stars and getting the distances through the parallax, which is, of course, the apparent movement of nearby stars with respect to background stars as the Earth goes around the sun. Gaia is in L2. But it's also looking at proper motions and radial velocities of the stars. Here's an example of the latest release showing the nearest 40,000 stars, how their movements will go over the next 400,000 years. So I'm pointing that out because that's where the release is. What's interesting for the extinction mapping is the fact that there are 1.8 billion sources in this latest release. And there will be quite a large number. The number is not yet determined, but with extinctions already derived in the catalog. So that should be out early next year. So what's Gaia good at? As I've just pointed out, it's very good at getting accurate distances. Here is the result of it's using the parallaxes along with the galactic prior to try to get more realistic distances in the plane. And you can see here the plane looks to be filled with stars. Great. Gaia is giving us a good galactic plane survey. But you have to be careful because that's what Gaia is good at. But what it's not so good at, the fact that it's invisible. If you look at, instead of looking at the plane of the galaxy, you look at along a slice, well, along the edge, if you like. So this is Z direction going up and down. You can see that if you look at where the galactic plane is, this little green slab, the stellar density drops off quite quickly after about 2-3 kiloparsecs. This is a log scale, so really it's not going to give us a lot of information in the inner galaxy in the plane. It is going to help a bit with diffuse interstellar bands, which I know are an interest to the PCMI community. I'm just piggybacking on this absorption band in stellar spectra because it happens to correlate, well, some diffuse interstellar bands correlate well with stellar reddening. Many ground-based surveys have been making catalogs of these DIBs. To date, the biggest catalog is about 50,000 measurements, but Gaia, the DR3, so coming out next year, may deliver as many as 500,000. So this could give us another way to map out the extinction in the solar neighborhood, especially. Okay, so there are other surveys, like I said, other data, but those are the main ones that I want to talk about. So what are current maps? What do the current maps look like? So I'll start with what I did in my PhD, so a few years ago now. The way this extinction map works is to compare a model with observations. So if you look at a color magnitude diagram of a galactic model with no extinction, it could look like this. And if you then look at observations, you see it's not quite the same distribution because stars are, when they're extincted, they become redder and fainter. So one could try to find the extinction that one would have to apply to the model for the model to be in agreement with the observations. And that's what I did. Producing a map like this with the galactic center in the middle of the plot and the solar position at the middle left. So this is a map that goes out to 25 magnitudes extinction in the V band. I'm pointing it out now in the current maps because it was the first reddening map in 3D of the galactic plane. And it's got an angular resolution of 15 arc minutes, which is not great. And it's got these structures that seem to point towards the sun because distance uncertainties are much higher than the angular uncertainties. No anti-center and little information below 2 kiloparsecs. But there's an update, which I'm hoping to submit shortly. And that's on the left, where the anti-center is included. It's the same data, a slightly improved galactic model, a much better color bar, I think, but that's personal, I guess. So what you still see these structures that seem to be pointing towards the sun. But if you look at local overdensities in this map, basically comparing the density just compared to the neighboring densities, you can start to see some of these structures may be explained by spiral arms. I think particularly with the Carina arm here, Sagittarius, even Scutum seems to match up quite well. Scutum crux. So this might be giving us some idea of what the large scale structure of the galaxy looks like. There are plenty of other structures that are not in spiral arms. I think that's just a fact of our galaxy that we have to get used to. Comparing it to the old map as well, this is a different projection, more Cartesian projection, where we look at longitude, slices, and distance. This is the way the method works, in that you look at one line of sight, one longitude, you get a distance distribution, and then you move along to different longitudes. And it's a bit easier to see how structures line up along different lines of sight. And you can see the big improvement. The top is the new model, and the bottom is the older one. And so many structures become more coherent, and you can follow them around a bit to see how the different structures connect between themselves. Okay. Gaia, as I mentioned, is getting stellar parallaxes. You might think, well, we can get the spiral arms from there, at least the ones that are close to us. This was a study that came out just this year, looking just at upper main sequence stars and some classical C-feeds in open clusters, about 1 million stars. Here's the density distribution in the plane of the galaxy. And so you see some things, but once again, if you look at the overdensities with respect to this local stellar density, some structures come out and you see maybe we're seeing some spiral arms here. Now, some of them are definitely spiral arm structures. However, I want us to be careful as Gaia is heavily impacted by extinction. If you look at the overdensity map of the Gaia stars in the top and the extinction map at the bottom, in fact, there's quite a good matchup for some of these structures, right? So some of them seem to be, some of the structures you see in the stars are driven by extinction and not necessarily by real stellar overdensity structures. Okay. So I'll move on to other extinction mapping, a different technique, which is what Roselyne Lallemand did. This is her latest version of the map in 2019. Now, the difference here, there's no galactic model. You just have stellar pairs, extinction distance pairs, and you then do an inversion to try to see what is the structure that would reproduce the observed extinction distance pairs. Here she did it in a hierarchical way, starting at low resolution and moving up to higher resolution at each step. Here she uses 2 masks in the near infrared and Gaia in the visible, but they're subject to a cross match, which means Gaia stars that are not in 2 masks or vice versa, you lose them. So your extinction maxes out at 4 AV instead of the 25 that you could get from 2 masks, because Gaia can't see that far. But there's a spatial resolution about 25 parsecs, no or fewer fingers of God, but the information is restrained to roughly 2 kiloparsecs from the sun. So it's a higher detail, but lower reach extinction map. And of course, you can slice that map in different ways and have a look at what happens in the different longitude, latitude, and altitude slices. Another method is published by Greg Green. Again, this is his 3rd version, I think, which is another approach where you're looking at individual stars. Again, it's a cross match between pan stars, 2 masks, and laterally with Gaia. And the idea here is to look at individual stars and try to get a probability density distribution of the star in distance extinction space. You can basically get constraints on where the star should be in terms of distance and extinction. And then you can get many stars along the line of sight, you superimpose them, and you end up seeing a ridge of extinction that comes out of high probability, and this gives you the line of sight extinction distribution. Similar extinction as Lallemand, a variable resolution. They're very good at communications. So they did this on their website. You get a little movie showing you see the parallax effect of the nearby clouds quite well there. So it's very pretty. And if you look at the top down, so from the North Galactic Pole, there's the distribution of dust in the plane of the galaxy, going out to about 4 kiloparsecs. Nothing in the 4th quadrant because pan stars, and there's, it's in Hawaii, so you don't see that part of the sky. And yeah, you don't get out very far in the plane. In fact, if you look at the maps, this is the same physical scale. You can see that the map that I've done has got a much bigger reach in the plane compared to the other ones. But then if I want to be fair, I can try to compare my map on the same color scheme and scale as the green. And you can see that indeed within 2 kiloparsecs, predictions are not as good. So there are a few other maps I didn't get into, so I don't have time to go through all of them, but there's an overview of maps that are being done now. And I could go on now to the last point, which is where are we going to go? What kind of data do we need to do something a better job? And in fact, before I go on to surveys, I want to mention the work from David Cornu. Just finished his PhD last year in Besançon. And what he did is he looked at 3D extinction mapping using convolutional neural networks, so machine learning. And the reason I'm talking about him now is that he used 2MASS and the Besançon model, same thing I did. And 2MASS, like I said, has been around for a couple of decades now. And using a new improved method, he's able to get this image on the left. He just did it for the Carina arm segment compared to my recent results here. And you can see that you get a much cleaner map where the structures are a bit more obvious. Now, it's difficult to generalize to the full sky, which is why it's only in a certain bit here. But what's interesting as well is the machine learning can use multiple surveys without cross-matching. So you maintain the information in the near infrared of all the stars, and you gain the benefits of Gaia parallaxes too. So what I mean to say is there's still a lot we can do with old data. We've got lots of it. As far as ground-based surveys go in the future, there's not a lot that I'm aware of that's getting prepared. The largest current near-infrared survey, like I said, is 2MASS, but with a seeing that's not very great, not very well matched to the visible. WFCAM and VISTA, very good surveys. Euclid's coming, but that's going to be extragalactic as well. So I mentioned that WFCAM and VISTA are heterogeneous. Here are the different surveys, the footprint on the sky. But there's an effort to stitch these together to get a homogeneous survey across a large fraction of the sky. Just missing the higher bits up here because WFCAM can't do it. But we'll have data down to 18.2 in the K-band and a seeing under an arcsecond. So that should be coming out shortly. That could be very useful. Otherwise, at a more future timescale is the idea to do Gaia again, but in the near infrared. This would be in the H-band or perhaps in the K-band. And this would give us 5 to 6 times as many stars. And at the top image here, you see the ratio of stars in this new infrared survey compared to Gaia. And so green is giving you 10 times as many stars, red 100 times as many stars. So it is mostly in the plane because Gaia is getting quite far above the plane. This is not taking confusion into account, so it might not be quite as good as this, but certainly going to be many, many more stars, especially in the plane where we can get out to really see the galactic bulge in its entirety and maybe even to the far side of the galaxy. Okay. So while in Japan, they've had this idea for a while too, called Jasmine, but it was a very big project. And instead of waiting to doing the whole satellite, they've decided to do a kind of smaller version, which should be launched sometime this decade. So like Gaia in the near infrared, that sounds wonderful. But the main objective is galactic center archaeology. So they're going to be focusing on about 2 square degrees maximum towards the galactic bulge. So it won't enable us to do these big extinction maps, but it would be very interesting already to see what kind of information we can get out of a survey like that towards the galactic center. And the last one I want to talk about quickly is the Nancy Grace Roman Space Telescope, which was previously known as WFIRST. Likewise, launched sometime this decade. And there is an idea to do a galactic plane survey, which would be like a glimpse with Spitzer, plus or minus 2 degrees in latitude, and the full 360 of the galactic plane. And it should be 3 magnitudes deeper than 2 mass. Here at the bottom, you can see what improvement we should expect with WFIRST compared to 2 mass on the same size. You can see we get deeper and much higher resolution. So this should give us a homogeneous survey in the near infrared across most of the galactic disk. Okay, well, to finish, I want to say that 3D maps, of course, are important, as I hope you agree with me, for galactic structure, but also looking at observations at the ISM. You need to know where the things are, how far away, so you can attach physical properties to the different observations. Gaia is certainly a huge help, getting higher resolution and distance, but it's not going to be a great help in the galactic plane, and future surveys should help quite a lot with that. Thank you.
Thank you, Doug. I think Jerome has a question.
Yes. So first, I probably missed it. What is the angular resolution you or the linear resolution you get with your method?
In terms of the distance uncertainty?
No, I mean, for instance, Rosine has a typical resolution of 25 parsecs, and the question is, do you achieve better or similar?
Oh, not as good as 25 parsecs. The binning already is at 100 parsecs, and often structures are spread over a couple. So I'd go to a few hundred parsecs probably.
And I have it's also a detail on Perseus. You said that there is a gradient of 16 parsecs. Is it of the same order of magnitude as the size of the filament?
So that's a good question. I'd have to do a small back of the envelope calculation before answering that. But
okay.
Thank you. There was a question by Caroline online.
Yes, I was wondering, you mentioned very briefly Euclid, and I was wondering specifically for 3D extinction mapping, what you expect to get from Euclid that you are not able to get yet.
well, as far I don't know how useful it will be because it's avoiding the plane. So Gaia is already giving us a full sky, pretty deep considering the extinction that is present at high galactic latitudes. I'm not sure we're missing many stars there. So if Euclid had dropped a bit in galactic latitude, I think then it would have been more useful. But as it stands, I'm not expecting much in terms of 3D extinction mapping from that.
You. There's a question by Ludovic as well.
Yes, you mentioned the diffuse interstellar bands and all the mapping around that. So it's a question from a non-astronomer. And so what is preventing their identification? So you have some ideas or some additional complementary observation that could help?
I think that the knowledge to answer that question is somewhere in the room, but I'm not sure it's me. Like I said, I'm interested in this band uniquely for its capacity to trace interstellar extinction, but I haven't looked into the identification of the carriers.
Does anyone want to comment on that? All right. Thank you very much, Doug.